Yeah, good. All right. So this I really love is sort of one out of the lecture, sort of a summary of, in nice colors, the ionosphere itself. Altitude is the vertical axis, wavelength is the horizontal axis in nanometers, so we'll have to multiply by 10. And the colors indicate the deposition of energy, how much of the sun's radiation at each of those wavelengths is deposited at which height. And you can see this sort of tendency for these wavelengths, which are all shorter than the visible, right? The visible starts at maybe 4,000 or maybe there's, yeah, so 3,000 angstroms. So there's a little bit of violet in there. And then it really goes down into the ultraviolet. And the deposition of energy is fairly low down in that case, sort of around 30 kilometers. And you can maybe up to 50 kilometers. And that's, first of all, from the spectrum along the bottom, which just shows you how much light there is at each wavelength. This is a log scale. So of course, the vast majority of light is in the visible, which is why our eyes work the way they do. Because that's really where all the light in the sun comes from. But there is, enough in the ultraviolet and then tapering off to the extreme ultraviolet and the X-rays to do something to the atmosphere. That sort of 2,500 angstrom peak is what's showing up at 50 kilometers. That's actually leading to this bump in the temperature profile, which you see all the way along the right. So that is sort of significant, but that's really not what we're going to talk about, because that's not the ionosphere. It's up higher where you're starting to absorb wavelengths like 1,000 angstroms, 500 angstroms. That's all happening up at the 100-kilometer range. And also for the purposes of space weather, you see that if you had a black body spectrum, it would just basically be zero by there. And this is all coming from the 1,000,000-degree corona, all this very short wavelength. So with that being said, here is a picture, here's a figure of 2.5 out of the book. And we see the different species and how they decrease with height. In this case, again, altitude, it's really difficult to avoid the temptation of making altitude the vertical axis, even though we like to use it as sort of the, we use it as the independent variable. It runs up and down. So, and you can see that we have, here they only plot 3 constituents. Good old nitrogen, which is what our atmosphere is mostly made of. Oxygen, which is very important for life, oxygen molecules, O2, and atomic oxygen. And the first activity I talked about, I pointed some groups to, was this question of why is there no atomic nitrogen? There's atomic oxygen, which you obviously get mostly from breaking up molecular oxygen, O2, and dissociating it. And just as a curiosity, I know I've actually saw some people with backgrounds that were these nice aurora, and you see these nice green images. This is a view of the aurora in Bozeman, not recently. This is during the winter, and this is during a period when we got, had nice solar storms. This green line is in fact atomic oxygen. And so you can already see that up where the aurora is being formed, atomic oxygen is pretty abundant. And in fact, for everything above 200 kilometers, it's more abundant than anything else. So does anyone from one of the groups that looked at this have an answer as to why we don't see atomic nitrogen, N by itself? Okay, nobody, did you guys do this exercise? Someone did. Activity 17.
Yeah, we found that the binding energy of N2 is so low that nitrogen has a tendency to want to bond with itself quite readily, just because it doesn't take much energy to form the bond compared to like O2 or H2O. So therefore, you wouldn't have a lot of atomic nitrogen just because it wants to bond with itself so much.
Right, right. I mean, here's the bond energy. So it's actually, you know, it's a high number. It's almost 10 electron volts, and that's the sort of, yeah. It's a low negative. It's a low negative number. That if you were to express it as an energy, it would be -10. So it takes 10 electron volts to break that triple bond in nitrogen, and only sort of 5 to break the double bond in oxygen, or even the double bond in CO2, to sort of give yourself carbon monoxide in oxygen, if that's what you tend to have. So yeah, you will see you will see atomic oxygen, because you can break those bonds with 5 electron volts, but not much atomic nitrogen because it takes a lot more energy. Does anyone remember the wavelength of light you're going to use to create a 10 electron volt photon?
Professor, so we cannot see the emission from the nitrogen because they are much bond in their.
Well, it's not that the emission was kind of this is just kind of a cute side note. The important thing is to look at the graph on the left and see that these are the things that make up the atmosphere when you're at, say, 500 kilometers. It's atomic oxygen mostly, molecular nitrogen, and then molecular oxygen. So there's 3 things up there. And my question was, why is there not atomic nitrogen as well? Why aren't there 4 different species? Because there's certainly a lot more nitrogen to work with. The N2 is much higher than the O2. And the important thing is that the only way you create O is from this radiation. Right, you need these photons to come in and break the bonds and take your molecular oxygen and turn it into a pair of atoms. Now those will recombine, right? So it's not you don't just do this once and then dust your hands off and say you're all done. Okay, does that answer your question? So it's not that, I'm not saying the emission is a problem. I'm saying that the existence of the stuff is a problem. All right. Well, that's a side note. I want to break us into groups.
Hey,
Kelvin,
yeah. One quick question before you go on from that slide.
Yeah.
The O on the picture is oxygen. Is that?
That's what I've been told.
Yes.
Yeah, this is atomic. Not O2. This is atomic, pure, just atoms of oxygen. I'll also say, since this is a NASA summer school, there's a group here, pretty unique, that studies the chemistry of atomic oxygen working on spacecraft. And it is bad. The one thing if you build something, the one environment you don't want to put anything that we make with our machines or anything into is a pure oxygen environment. It just corrodes like mad. But that, like it or not, that's what you're in. So atomic oxygen is a big deal out there, like it or not. And here's the sort of explanation for why. The photons are constantly dissociating the molecules, and all you need is a sort of 6,000 angstrom photon to have this much energy, and you're gonna, 2,000 angstrom photon to have this much energy, and you're gonna do it. Okay. This is sort of even more important in that graph. So I'm going to break you up into breakout groups, and I think a lot more of you did activity 9. So there will be people, I think, in every breakout group, in every synchronous group, who've worked on this. And it more or less asks for this thing here, which is the pressure scale height. It is the temperature over the molecular mass, the average mass, the mass of a molecule, divided by Ng. And the the various things they ask for. They ask for a lot of things. Let's just focus on Earth and use the surface temperature of Earth. And if we're down at the surface, we are really mostly dealing with N2. On Venus, you're mostly dealing with CO2. The surface temperature is quite a bit higher. And the solar photosphere, because this is one of these ubiquitous phenomena, right? This pressure scale height appears everywhere in all areas that we deal with. So I'll break you into breakout groups. Let's break up for 10 minutes so that you can spend 5 minutes getting to know your new group, and then another 5 just coming up with these 3 numbers, the pressure scale height. And if you worked on many more numbers, that's fine. But pressure scale heights of the Earth's atmosphere, Venus's atmosphere, and the solar photosphere with these numbers. And I'll leave these numbers up. I think you'll be able to go back and forth, or you can just take a screenshot or something. Okay, Kelvin, are we ready to break up to
Yes, we are.
breakout groups? Okay.
Can I double check? Let's double check one thing. First, everybody should have found their new assignment for their breakout groups. Is that true? So it should only be 4 people in a breakout group. Okay, great.
All right.
And then, as Dana said, take a little bit of time to introduce yourselves and share your item that you, your object that you had, or some object that you have handy that you can show to your group.
Okay, so yeah, Kelvin, let's do this timed for 10 minutes.
All righty.
Join us back here in 10 minutes.
Okay,
right.
I'm opening up the breakout rooms now.
Okay.
Hello.
I see that a couple of you are in the main room. I'm going to try to send you to your assigned breakout rooms. All righty. So. Good morning, Veronica. Okay. Good, she's in a breakout room, all righty.
So I'm going to share my screen again. So do we have any questions from when people were doing this, or should we, oops. Can I just call on group, eeny, meeny, miny, mo, group 5? Anyone from group 5? Just these 3 numbers. I know, you know, you were asked to do a bunch of different numbers, and maybe you did even more than that. How about the pressure scale height on Earth, or our
Earth. On which height? At the surface?
at the surface? Let's just start with the surface.
Yeah, that's 8.73 kilometers.
Okay, good. I just wrote down 9. Yeah, as I pointed out to several people, that really is about the height of Mount Everest. So, you know, you're 1 scale height above, which is why air is so thin there. How about Venus? Much higher temperature. The molecules are a bit heavier. Gravity this is really Earth's twin. Gravity is almost the same. What did group, let's ask group 6. What did you get for, did you find a scale height for the surface of Venus? Anyone from group 6? How about anyone from any of the groups? Just shout out a scale height.
Sorry, I had to unmute. We got about 15.7 kilometers.
All right. I think I might have been a tad low, but 15 kilometers. Excellent. And group 8, the photosphere.
Around 180.
180? Yeah. So there you have it, 180. Now for Earth, when you go up and actually look at the part where we're going to start talking about the ionosphere, now we're in the thermosphere and the temperature has really risen up. So instead of 8 kilometers, the nitrogen molecules have a sort of 43 kilometer, and you can more or less see this is 5 times room temperature. So the scale height is about 5 times larger. Falls off at 43. You can see there's our good old atomic oxygen. The reason atomic oxygen is so prevalent is that it has a mass that is so much lower that its scale height is 76 kilometers. So a larger scale height means you have to go a lot higher before the density has fallen off much, etc. And here's a picture of the same going on for Venus, at least. And here is one thing that they alluded to, and this is just bringing us back out of the ionosphere and talking about the sun. We have this 180 kilometer scale height, which basically means the density of the solar atmosphere at the photosphere is falling off by 1/E every 180 kilometers. So if you can imagine having to go 3 of these 500 kilometers before the thing has fallen by 95%, and that's basically going from full to almost nothing. That's 500 kilometers. That seems like a large way. It is 0.0007 solar radii, right? It is nothing compared. That's why this image looks so sharp. Also, you could point out it's 0.7 seconds of arc viewed from Earth. And even, until you get into adaptive optics, it's very hard to resolve such a small scale. So that's one of the reasons when you see an eclipse, you see this nice knife edge, and you can start to see even the moon's mountains creating these nice little Bailey's beads. Once it's happened, though, and this is something I think not a lot of people give thoughts to, because it was known, you knew once the surface of the sun was covered up, you saw this beautiful corona, right? And that's really where the name comes from, because it's this beautiful crown around the sun. It's falling off a lot slower, right? Even if you account for the imaging effects and things, the scale height of the corona is much, much greater than 180 kilometers. You see this with your naked eye. And here's the scale height. And the 2 things we could imagine changing are the temperature or the mass. And for a long time, let's say all through the 1800s, nobody knew which of these 2 things was different in the corona. We now know that it's actually the temperature. But at the time, does anyone know the story of coronium? Right? At the time, there was quite a distinct possibility that this thing was made out of a material that was much, much, much lighter than hydrogen. That M was much smaller than the mass of a proton. Now, to you, that sounds crazy because you know the periodic table, but they didn't have the periodic table. They didn't know atomic structure. They didn't know, they couldn't solve Schrodinger's equation because it didn't exist. So they had no idea whether it was just a much lighter stuff or it was a hotter temperature. But we now know that it's the higher temperature and that this is really made out of the same stuff, really. All right. So, let's see. I think before we start in on activity 19, yeah, we'll have to do that soon. But this was activity 19, and it really goes to thinking of the optical depth, tau, which is this integral. They don't actually write it down. I'll show you the integral in a second. And we want to show that the optical depth could also be written this way in terms of the pressure scale height and the density and chi. And chi is the angle from the vertical of your line of the path of the photon. Okay, but the important thing is that the probability of suffering 0 absorptions is e to the minus tau. And I'll just go through this because it's worth basically going through an argument like this for collisions of every kind, I'd say, you know, once a year for your professional life, just reminding yourself how this works. So what you're really interested in is you have all these absorbers, right? And let's not even talk about what they are, but you have a path the photon would like to take. However, it might get absorbed. And every absorber has a cross section, right? A cross section for absorption. And you want to know if you're going to make it through without being absorbed. Well, a sort of more concrete question to ask is, if I just follow this path, how many absorbers does it go through, right? How many times does it pass through the center of one of these? These are supposed to be spheres, but their cross-sectional area is pi r squared, so they're more like disks. And it's a tough question until you realize it's the exact same question. Answer is exactly the same as if I ask, what if I take that center and put a disk around it of the same area and form a cylinder, okay? So instead of thinking about all these as balls, I'm gonna think about them as points. These little purple things are really supposed to be points. And I'm just gonna ask, how many points are in my cylinder? Does everyone see that? So that's the question we want the answer to. If I create this cylinder, cross-sectional area sigma, and then it just goes on along the length S, how many points are in that cylinder? And what I need to know is, what is the volume density, the number density, number per unit volume of points in that cylinder? I mean, I'm sorry, of points. And then I'm simply going to integrate that density along the cylinder. So integrate the cross-sectional area to, does everyone see that? Does this make sense? This is how you answer that question. Actually, what this gives you is the average number. Okay, because the density is kind of an average, right? It might vary along the path, but it's telling you sort of on average how many points are in a given volume. Then what you have to do is you have to take this average number, which we'll call tau, and say, now for a given cylinder, what is the probability of having exactly n points in it? Okay, and this is one of the reasons we should always be doing this exercise, is you have a distribution of things, right? Tau might be not an integer. It might say there should be 7.2694 centers inside of it, but you're never going to see 7.6, you know, et cetera, in that. You're going to see 0, 1, 2. So is everyone familiar with the Poisson distribution? Very important in all physics, very important in all of life, right? If you want to know about counting things, this is the distribution for things when you count them. And it is tau to the n, the mean number to the n, over n factorial e to the minus tau, right? So whatever tau is, this will tell you the probability of seeing a given number. And obviously, as n gets really, really big, n factorial is going to get enormously big, and the probability is going to go to 0. You're just not going to see any, you know, if the mean number you see is 7, you're not going to see 300, right? That's going to be 1 over 300 factorial, and it's just not going to, it's going to be 0. And then here's the last bit of the argument. The probability, the question we're ultimately interested in is, what is the chance the photon gets through? Which is the same as saying, what is the chance that there's 0 absorptions? Which is the same as saying, what is the chance that there are 0 centers inside my cylinder? And that's easy. I just put in n equals 0 into this formula, and I get 0 factorial, which we all know, although we may not be happy with it. 0 factorial is 1, and tau to the 0 is 1, and we have e to the minus tau. Everyone see that? So it's really, there's almost no physics involved here. This is just geometry. But that tells us, once I've calculated this integral sigma number density ds, that is what we call the optical depth, where sigma is the cross section for absorption. Okay, so the activity is that now you've seen this. The intensity at h is then an integral from infinity over the number of absorptions along the way. Combine that, we want to actually derive this expression here, right? This is not an integral, and somehow it's related to that integral. So the first thing I want us to do is talk about that, and then use this and this to figure out this, which is basically going to be the shape of the ionosphere. This is the number of absorptions going on at any given height, right? And so that's going to show us the shape of the ionosphere. So Kelvin, are we ready for one more breakout?
Yes, we are, Dana, and I can open those rooms right now.
And this is just 5 minutes. We'll just do
5
5.
minutes.
So
Already.
just, yep. And I'll see you all back in 5 minutes.
Okay, opening
Okay.
rooms now.
Yep. And we're all back. So any questions on that? Or just answers? Let me just quasi-randomly choose group 7 to tell us what you did to get these expressions. Someone from group 7.
Pucha, what do you think? Should I or should you?
You can go. You can go. You should.
Okay. So maybe I can share my screen. It makes it easier.
You should be able to.
Yeah. Now you can see it probably.
Oh yeah.
Okay, so I just basically followed the instructions. I'm not sure if I was supposed to do anything more than that. So
Nope.
Here we have the equation given, then we had the probability of survival. And then the optical depth was defined as the mean number of absorbers within the cross-section along a photon's path from infinity to height h. So I'm integrating from infinity to h the cross-section times the number density, which defines the number of absorptions, and then along some path. And we have this path here. Okay, I can show it like this. Okay, so if we have like the surface here, and we have height defined as going upward from there, we can write this path dl at some angle like this. And then we put that into the integral and basically use this form from for the density, how it scales with the scale height. And calculating that, we get the form that we wanted. And then if you have some intensity at infinity and you want to know what is the intensity at h, you multiply that by the probability of kind of that intensity that has survived till that height. So it's like this. And then I just inputted everything into the equation.
Excellent, excellent. All in one page, that's great. Any comments? Anyone from other groups see this and want to make a comment on it? Looks pretty airtight. All right, thank you. Thank you, group 7. Thank you, Laura. So, okay, great. Then we will just, oops, yeah, here we go. This should do it. So this is what we just heard, so I won't make you go through. The important thing then is what really happens, depending on what these cross sections are, and here on the bottom left, I show kind of derived what the cross section for absorption is as a function of wavelength. And you can see there's a very large cross section of absorption if you are photon of 50 nanometers, so 500 angstroms, or even 1,000, 100, 1,500, you know, this whole range has absorption cross sections which go down to 10 to the minus 20. And essentially when you put in this simple form with the scale height we derived, but this is actually for higher temperatures, you see the photons don't make it. And that's really what you're seeing over here. The photons are absorbed right there. And
hey, Dana?
Yeah.
Before we go too far, Gwen has a question.
Sure, yeah, let's hear.
Yeah, I think it's pretty difficult to like calculate the cross sections. Can you like comment on that maybe?
It really is, yeah. It's difficult. It's not something I've ever done, but you know, it is one of those exercises that you get in graduate quantum mechanics. You're really trying to find the probability of a transition from a photon plus an atom in the ground state to an atom in the excited state, right? So we all know that that's some horrible integral with, you know, a bra and symbolized by a bra and a ket and a operator. So in principle, that's all you have to do. In practice, that's a horrible integral to do, and all I can do is count my lucky stars that someone has done it.
And these things are tabulated someplace.
And they're tabulated, and yes. Also, let's give credit to the fact that that's just a theoretical calculation. You can do experiments and, you know, measure these things, and they're also measured. But yes. But I think the important thing is to know that such a quantity exists, and it depends on wavelength for reasons that the theory tells you a bit about. That is, if you have a very high energy photon, there are many excited states you could go to, including states where the atom is actually energized. Let me see. I think I have, yeah. So there's possibilities of ionizing a nitrogen molecule, ionizing an oxygen atom, ionizing an oxygen molecule. Those are all, you know, take a finite amount of energy, and you can see that the absorption cross section around that is very high. And so that's what gives you this very high height of absorption for those particular processes. The last thing I wanted to point out is when you're doing this ionization at all these different wavelengths, that Q that you calculated is actually, I love this, and you heard it in my lecture, how much I love having a function that is an exponential of an exponential. I'm just that kind of nerdy guy that functions turn me on, and this is a pretty unusual function. And this is a log plot of that, and it just looks like it just falls to zero so rapidly. It's just a floor. And that is sort of the structure of where you are doing all your ionization if you're ionizing, or when you're doing all your absorption and heating. And so this is the important profiles that you're going to see. And you can see for this particular 2500 angstrom absorption, that's essentially the deposition that's creating the stratopause right there. That's where all that heat is coming in, and that's why the absorption is so focused there. It also shows you why, if you follow this curve, it goes from yellow to black on the bottom really sharply, and on the top a little more gradually, right? I mean, there's a lot more space between the yellow and the black on the top than the bottom, and that's really having to do with this great function, this exponential of the exponential type function. Because as this exponential gets larger and larger, it goes into an exponent and just makes this thing with a negative sign.
And Deb has a question as well.
Yes, okay.
Yeah, I just want to ask you, in the sigma plot, in the
Mhm.
Lyman alpha line, it is like steeper. The other parts are smoother. So I want to
Yes.
ask why.
I don't, I don't actually know. I mean, I think I may have inverted this sigma plot from something else. So that may actually be my own plotting artifact. But I believe there's a lot of structure in the absorption there. But I can't, I wish I could tell you more. I really don't know. You can see evidence of that over here, but of course,
Yeah,
this is also
also
there.
there. It's really
Sorry
like
about that.
fluctuating. Okay.
This is just, and before we took a break, I wanted to go back to another, I think it's an activity, let's see, but I'm not going to break out for it. Yeah, this is the activity. And this is just to show you this idea of optical depth is pervasive in heliophysics and actually in astrophysics as well. For the planetary atmospheres we've been talking about, it's the probability of surviving to a height h if you start at infinity. If you're doing stellar atmospheres, the photons come from inside the star and go out to infinity. They're only observed because you are in infinity. So we actually interpret e to the minus tau as the probability of a photon surviving after originating at a height h. So in both the things that I've been plotting here, tau equals 1 is this dashed line here. That is sort of the average height of death of your photon. So you can see that you have a probability 1, very close to 1, of making it down close to that tau equals 1. And you have a probability 0 of making it very far beyond tau equals 1. And that's because e to the minus tau, goes from 1 to 0 as its exponent goes. So tau equals 1 is usually identified in the ionosphere as that place where those photons are basically going to die. And in astronomy, it tells us where those photons were born. Now, of course, they're not really born, they're scattering all over the place, but the ones you observe at our nice comfortable place at z equals infinity have by and large, on average, come from the place that tau is equal to 1. And so I know some of you actually were assigned to look at this question. That is, we see a solar disk like this, and it's bright in the center and a little darker. This is a colored image, but it's a little darker out at the edge. That's what we call the limb. And the reason for that is that it has to do with this chi in the denominator, cosine of chi in the denominator. When I'm looking close to the limb, right, the photons are going at a very steep angle, at a large angle relative to vertical. And so cosine of chi is a small number. And that basically makes tau large, or tau equals 1 appears higher up in the atmosphere. So when you look at the limb of a star, you're looking higher up in the atmosphere than you are when you look at the disk. Okay, we know that this atmosphere falls off at, over 180 kilometers. So the difference between the tau equals 1 surface here and here is only, is 50 kilometers or so. But apparently there's a difference in the atmosphere 50 kilometers up. And the answer to the question, well, then you take into account the fact that when you look at this image, what's bright is actually hot, because the black body spectrum gives us more photons from a hotter region. So the center of the sun, when seen on Earth, is hotter than the limb. Now, that's a very geocentric viewpoint, right? Like the Earth is attracting the hottest part of the sun. What it really is when you look at the limb, you're looking higher up and you're seeing a cooler part of the atmosphere. So what can you infer about the stratification of the solar atmosphere from the fact the sun is brightest near disk center and darkest towards the limb? You can infer that the temperature is falling off with height. Did anyone who, yeah, so that's what limb darkening really tells us about the temperature structure of that layer of the atmosphere. Did anyone who attempted activity 18 get that kind of argument or puzzled by why you should have gotten that argument?
No, but can I actually ask a question that has to do with the activity?
Sure, yeah.
The very last question is talking about, on average, the EUV on and off the limb.
Yeah, I cut that off, right?
I didn't, I mean, in my opinion, like the answer is trying to ask us like, well, obviously the optical depth must be higher on the limb than off the limb.
Yes.
But
no, wait. So let's, yeah, so this is slightly different because at that point you're dealing with an optical, you're dealing with a line of sight that doesn't actually go into the center of the star, but just skims across the surface and then goes off to negative infinity. Or I guess it's infinity to minus, yeah, negative infinity. Sorry, I don't have a nice picture to illustrate that. So basically, if you, wait, I think I should be able to annotate. Can I annotate? Oh.
You should be able to, yes.
Yes, annotate. Good. Right. So here's my drawing utility. Here's a line. So what you're asking about, we're now going to imagine we're over here looking. Okay. There's my little eye. And I see a line of sight that goes like that. And I'm supposed to integrate over that line of sight. But if I look across the limb, I integrate over that line of sight. Yeah. Does everyone see that? So, and the other thing is when we're looking in the EUV, the photons we're talking about are photons that can't really come from the photosphere. We're talking about photons that are, you know, produced only at temperatures of 100,000 Kelvin. So the photosphere is dark, but there's a layer above it, the transition region, and you're seeing through that. And so just imagine you have some, let's see, you have some, and I'm going to change the color here. So we're now doing blue. We have some. Okay. Now, Will, what can you say about the line of sight, the optical depth along the bottom path versus the top path? Does everyone see what I'm saying?
Sorry, I was muted. It's higher for the bottom path because you're looking deeper into the transition region.
Can you estimate a factor? I mean, based on symmetry, right?
2.
It's 2. It's twice as bright. Does everyone see that? So really, you're only going to pick up the stuff that's just within the blue region. And so I want to say on the bottom path, okay, I'm going to draw in yet another color here, a straight line in green. The bottom path, I'm picking up, say, this much. The top path, I'm picking up this much. So yeah, when you get to the limb in these EUV lines, you're seeing something that's twice as bright. The intensity just basically jumps by 2. All right, let's take a break and we can continue discussing this while we take a break. And let's get back here at 1/4 of, so in 5 minutes. Sound good? Okay. I'll stop sharing. Does that make sense?
Thank you. That's actually really helpful.
Yeah. You know, this whole discussion is very helpful. It's interesting to listen to solar physicists, you know, geophysicists, engineers, try and get this idea of scale height across and why there is a characteristic and why it's not fixed, because different atmospheres have different characteristics, but we can specify that 2/3 and 2/3 and 2/3 again in the same way.
Okay.
And Dana, did you say the words Chapman layer?
I
You did it in lecture once.
I did in lecture.
Okay.
I didn't. I showed the picture. I think the words were on the slide, and I did in lecture.
Which was
I get too
mystical to
focused
me.
on the function.
Which was mystical to me because everybody referred to Chapman layer and nobody like went through this explanation. I didn't connect the two for a very long time.
Oh, okay.
Oh, I see. Okay, a Chapman layer is just this simple model.
Right.
Yeah.
All right.
Thank you.
Okay. Yeah, sure. Everyone back. Let's see if I have any.
Can I also ask a question, Dana?
Yeah, sure.
Okay. First, I have a comment because you mentioned that the sun in the photosphere shows a limb darkening.
Yeah.
Apart from the off limb in UV, we also see a limb brightening in the corona in the UV images because of the reversed temperature gradient in the corona.
Yes, that's that's more in the far ultraviolet, in the ultraviolet. Yeah.
Yeah, EUV.
Right.
We see that.
Yeah.
And regarding the corona, the scale height. The scale height as given like this is a hydrostatic scale height. So,
oh yeah.
So we usually can't use it in the corona because most of it in the corona is contained in loops and in the magnetic field. So it makes no real sense to use a scale height in the quiet corona.
I disagree with that. I mean, if you actually look at coronal loop models, the atmosphere, the pressure does fall off if very close to exponentially with that scale height within a loop. Because the only force parallel to a magnetic field is the pressure gradient force. So the magnetic forces can't really help you. So along any field line, you will see the atmosphere fall off as long as it's static at that rate.
Okay, because I know from corona holes where it's, so I did some calculation there, and it seems, and also others suggest that it seems to be valid because we have the long open field lines and we have only the gravitational. But in the same calculations, I get problems when calculating the emission measure in quiet sun regions. So I get, if I use a hydrostatic scale height there.
Okay, yeah, right. So I guess I should mix up the theory, which says it should fall off like that, and the observations, which show it doesn't appear to. And there's a famous picture that Marcus Aschwanden generated by taking a nice image. I think it's the classic trace loop image, what they call oh no, now I'm blanking. Is it Cinderella loops? Anyway, and showing what they would look like if their density did fall off with the correct scale height. And why that doesn't happen is a complete mystery to this day. Nobody knows why the emission measure in the corona doesn't fall off as it should. People think that it might have to do with the under resolution of the loops. Yeah, but you're right. Theoretically, it should be falling off hydrostatically, but imaging shows that may be a bit of there may be more of a mystery there than people are always ready to address.
Okay, that also answers the question, what would be a better estimation of the emission measure from the solar corona?
And that may be a discussion for the office hours.
Yeah.
Because David's got about a half an hour to tell us about magnetospheres.
Right. That's about it. So let me just jump in then. We have the first thing we're going to talk about having to do with magnetospheres is shocks. And I think that topic has come up many times so far. I think in Amitava's lecture, he mentioned, you get these shocks with supersonic aircraft, but since this is a NASA summer school, I thought we should probably think about spacecraft, right? So when a spacecraft is re-entering the atmosphere, it is going, it's going at escape velocity. At least the Apollo spacecraft, which came from the moon, are going at 11 kilometers per second, which if you use surface temperatures or sound speeds, it's going at Mach 33. okay? And if you're one of the astronauts in the spacecraft, you're stationary and the atmosphere is rushing at you at Mach 33. And basically the idea of a shock is when the supersonic flow, the Mach 33 flow, hits an obstacle, and if you're a spacecraft, that's what you are, it generates a shock. And here's a nice image of what theoretically the shock around the Apollo spacecraft should be. And you can see what the colors are temperature. And you can see this nice blue, and this is the atmosphere before it encounters the obstacle. And it's all the same temperature, and it's all going at 11 kilometers per second. There's no variation in it. The shock will slow the speed down from 11 kilometers per second. And the second thing it does is it heats the fluid up. And these two things combine to basically mean the flow after the shock is subsonic, okay? So it's supersonic, Mach 33. The Mach number in the region outside is going to be much less than 1 actually, mostly because the temperature goes way, way up. The temperature goes up because all the kinetic energy of those air molecules heading towards you at 11 kilometers per second, a lot of that energy is converted into heat, okay? And it is only a subsonic flow that knows enough to go around an obstacle. Okay, so this is basically the idea. And you can see now that that's why right after that shock, you can see in this calculation, the atmosphere is 19,000 Kelvin or 20,000 Kelvin. That's hot, right? And you've all seen in the movies where the the astronauts are in grave danger because the space around them is 20,000 Kelvin, and it could, completely destroy their spacecraft. So that's, and I use, when I give this lecture to students, I play, clips from Apollo 13. The one thing I don't play is the part where the character tries to explain why that happens. And since they're a Hollywood movie production, they say, oh, it's friction from the air, right? Which of course makes my hair stand on end, what little I have, because it's not friction, it's a standoff shock. Right? And I guess they just can't say that to the general public, but we all know what heats up the air is not friction, it is a standoff shock that heats up the atmosphere. Okay, and that's basically the exact same story you get when you have the solar wind. We're talking about the fact the solar wind is going supersonically and it hits an obstacle like a planet. And the first thing we want to think about is a planet that has no magnetic field. So like Venus or Mars, that's just a solid object. And so it hits that and it has to go around. And just based on the argument I've said here, we get a standoff shock. That's called the bow shock. And here is a typical, this is an idealized picture of such a bow shock. This is an analytic calculation. I think we used to assign this as a homework problem for students in this class, but we haven't for a while. And you can actually calculate what this distance is. What's known as the standoff distance from a spherical, perfectly spherical obstacle in the midst of a supersonic flow, etc. For this, I want to get ready to do a breakout, and I want us to calculate what it is used. These are the conservation laws. So here we have curly braces, which basically mean the difference, the jump from one side, the pre-shock version, right? What happens in the supersonic flow minus the post-shock version. Maybe that goes the other way, but they're all equal to 0 because these are conservations. This is conservation of mass. So there's no jump in rho times the normal component of the velocity. There's no jump in this quantity. There's no jump in this quantity. And in all of this, what we're going to assume is the magnetic field is negligible. And in the supersonic, we're actually going to go into hypersonic regime, where in the region upstream, the Mach number is huge, and therefore the thermal energy is negligible. It's all kinetic energy, all bulk kinetic energy. Okay, so you're going to use those two approximations here. So they're say basically, right, and derive or show that the temperature is sorry, the way this all got cut off, it's 3/30 seconds of the solar wind velocity squared. Okay, Kelvin, are we ready for one more jump?
Yes, we are.
Okay, let's do 5 minutes. Some of you have worked on this, so let's get back in 5 minutes and talk about how we get this result. All right, see you in 5 minutes.
Opening up breakout rooms now. Veronica, I see that you're still in the main room.
We have everyone back. Let's just jump right in, and group 2, someone from group 2, could you give us a rundown of what you got?
Yeah, I can. Can I share my screen? It might be easier to do that.
Yes, you can. You should be able to.
Yes. So here, the problem explicitly asks to use all 7 of the Rankine-Hugoniot conditions. I just used 3 to start with to see if I got the right answer, because it's a little easier to do that.
Yes, I mean, if you're doing hydrodynamics, you only have these 3. Yes, and I don't think it really meant you were using all 7, but that's okay. You only need 3. Yeah.
Yeah. So I used the 3 for hydrodynamics, and after a bunch of algebra, you will end up at an equation that looks like this, where you have the ratio of the temperature T1, the downstream to upstream temperatures, in terms of the Mach number, that is the upstream sound speed to the upstream velocity to the sound speed, and gamma. In the shock limit, the Mach number is much, much greater than 1. So this equation 12 reduces to equation 13. And again, to get the answer that we want to arrive at, you have to rewrite this Mach number in terms of, again, this upstream velocity and the upstream sound speed. And then using the equation of state, you arrive at this equation here. And of course, gamma is 5/3 because plasma in this case can be kind of thought about as an ideal gas. And the mass is actually the average mass of the plasma, and which in this case is the mass of a proton over 2, because the mass of the electron, the other part of the average, is so small compared to that. So to a good guess, we can say that it's this. And this is a typo. This should be a 32. But that is the downstream temperature in terms of the upstream sound velocity. And this 1 should actually be the solar wind speed.
Yeah. Excellent.
Yeah.
Questions?
Yeah.
So what is the reason that we can skip the magnetic field terms here? I mean, I could probably understand the normal term due to the Alban Mach number, but how about the
so we're throwing away the plasma pressure upstream, right?
Yeah.
What is beta like in the average solar wind? Big, small? We actually talked about that.
Yeah,
a little
plasma beta is higher at the
very high. Yeah, it's like 10, or at Earth it's even
10.
higher than 10. So what does that tell you about the energy density and magnetic field compared to plasma thermal pressure?
It's very small, so you can just ignore it. Okay.
Exactly right. Yeah.
Thanks.
Yeah, sure. Any other questions, concerns?
Yeah. I have a comment, because what I found is not exactly matching the thing. So what is
Right. So let me address that. I think what probably happened, these are the equations, and you have to be careful using this equation here. So once we've X'd out all the magnetic terms, we end up with this first equation, the second equation, and the fourth equation. Those are the ones that Will showed.
Yes.
And actually, you can just use, if you use the factor of 4, you can just use this second equation. Will actually went through the exercise of deriving the last equation.
Yeah, I also.
You have to be a little careful with using the last equation because you have this extra factor of v multiplying all of this. So really using this 5.10 is more than you need. You just use this and you have only the kinetic energy, bulk kinetic energy, and the pressure and the bulk kinetic energy, or sorry, the ram pressure and the gas pressure, the ram pressure and the gas pressure. And if you throw away that, you basically can replace rho 2 in terms of rho solar wind times 4. And so actually with you have to use those other two equations to get this fact that the ratio is 1/4 or 4 for the different things. But this is the actual, once you use that, once you know that, this is the only equation you need, and you get 330 seconds.
Yeah,
Okay.
I think I somehow have some mistake on my thing because
Okay,
I
let's
got
talk about that
five
in the
time.
break.
Yeah, sure,
I
sure,
think
sure.
I think you know you can get a factor of 5 if you start using this because you have 5/3 over 2/3.
Yeah, yeah.
Let's get back to that over break or something, unless anyone else made the same mistake and got a factor of 5 different. No. What I wanted to, there's another part to this activity, which you may have done. This really has to do with where the flow speed, this you do have to use that other equation for, and you can figure out that we've just derived the temperature in terms of the perpendicular velocity, which at the nose is all of the velocity. But you can work out what the sound speed is and how that relates to the sound speed, because that's the temperature. And then you can see that actually the temperature, the Mach number will actually become 1 at some level, and that is 27 degrees. So let me just show you these wonderful diagrams using this Sprider solution. Essentially, this is the Mach number. And when you just go downstream, it's suddenly subsonic if you're at the nose point. But if you're over here, you have a perpendicular component of the velocity which drops, but the parallel component doesn't. And so you can actually be at a Mach number higher than 1. So there's only a region within 27 degrees of the nose where the flow actually decelerates to subsonic. Everything else, it stays supersonic because it comes in with some amount of velocity parallel to the shock and then keeps that. So this is the place where the solar wind, the temperature goes up by 330, or is this 330 seconds. There's another activity that people, some groups were encouraged to do, and that has to do with after you've passed the nose, you're in this subsonic region, and actually there's a place right at the obstacle. Here we're just thinking of this as a rigid obstacle where the flow speed is going to go to 0, right? When you come out here, it's only 1/4 of the solar wind speed. So it's down to 100 kilometers per second. It used to be 400 kilometers per second. So now it's only 100 kilometers per second. But by the time you get to the obstacle, it's gone down to 0. At that point, you have to use Bernoulli's equation. And that has to do with the kinetic energy and the enthalpy. Neither of these are negligible because now you're in a subsonic flow. And that is a constant at the nose, at the obstacle, the flow velocity is 0, and you have a temperature right there at the stagnation point. And then here's the number we derived. What you get is the temperature goes up a little bit. So the temperature at the very stagnation point, when you had all this kinetic energy and it's turned into nothing but thermal energy because the flow is decreased, has stopped, you have this one factor of 1/10 instead of 330 seconds. Now, does anyone have an idea of why it is not the case that you have this flow speed that's all kinetic energy, the hypersonic flow, and it gets stopped by the shock, and then the flow comes to rest right at the nose, and so it's all thermal energy. It has nothing but thermal energy in the flow. Why is it not exactly conserved? The amount of kinetic energy per unit per gram is not the same as the amount of thermal energy per gram when it's stopped. How come you don't convert it all to heat? Does anyone know? The factor of 1/10, yeah?
Because of expansion?
Right, or compression, if you will. Yeah, the work you do compressing the flow is also stored in the flow. And that's not thermal energy that's work. And that's why you end up using enthalpy rather than energy in these conservation laws. So yes, so you don't get 100% of the kinetic energy turned into thermal energy. A lot of it is turned into the compression. You've had to compress the gas. But here's the numbers you get. This is 7 million Kelvin. So you know, for a fast solar wind, 800 kilometers per second, the nose there, you're up to 7 million Kelvin, and at the stagnation point, you're up to about 8 million Kelvin. And the solar wind came in at probably less than 1 million. So the magnetosphere is considerably hotter than the solar wind, and it's because of this shock. Okay, so we really live in a bubble of extremely hot plasma, not yeah. Now, the last bit of this I want to talk about is the fact that if we're dealing with a magnetized planet like the Earth, Jupiter, or Saturn, we're not a solid sphere, but still you have to have the solar wind hits this magnetized object and has to go around it. So we still have a bow shock. But you also have, where does this, this is the magnetopause, where the Earth's magnetic field meets the solar wind. And the argument there is we go back to the nose point here and say, or the stagnation point, and say, okay, that has a fixed amount of pressure because it has been slowed down from the solar wind, and it has this very high temperature and enhanced density. So it has a fixed amount of pressure. And inside the magnetosphere, the only thing to overcome that pressure is magnetic pressure, okay? And so we do this simple calculation where you say the magnetopause must be possibly a sphere. It's a simple calculation to do it if it's a sphere. This is similar to the one Chapman and Ferraro did. And how far out from a dipole magnetic field that falls as 1/r to the 3rd power, the magnetic field does, how far out before those two balance, okay? And so you use a dipole field, and you basically, yeah, here's the real version, which has to do with image charges yet again. We've had problems with image charges before. And you get this expression, and I think I derived it in the lecture. This distance, known as the Chapman-Ferraro distance, is related to the distance of the object here and the magnetic field strength to the 1/3 power at the surface, and the ram pressure to the -1/6 power. Okay, so that sort of shows you how, just based on this balancing of pressures, how far away from the Earth the solar wind will basically be deflected. And then that magnetopause will sort of behave like a rigid boundary, and that's, you know, the standoff distance. The bow shock is out in front of the magnetopause by that distance. Okay, and this was, yeah, so if you put that in and you basically say, well, the Earth's magnetic field strength at the surface is 1/3 of a Gauss, and the Earth's radius, you put in all of that, and if you use a slow solar wind, you get a magnetopause Chapman-Ferraro distance of about 12 Earth radii. So that's where this thing here is going to be, about 12 Earth radii just using those numbers which we know for the Earth. And if you're in fast solar wind, and we use the same density, it really shouldn't be the same density, but let's just use the same density. It comes in just a little bit. I've doubled the solar wind speed, but you notice it goes to the minus 1/3 power of the solar wind speed. So that brings it into about 9. And there was an activity that some people did that was how much density do you need if the solar wind speed goes up to 2,500 kilometers per second? So 6 times the slow speed before you can push the magnetopause into a distance that would basically, it would leave geosynchronous spacecraft outside of the Earth's magnetic field, right? And so the first thing you need to know is where they orbit. And for that, you go back to Kepler's law. You know that for geosync, your period of orbit must be 24 hours. Maybe you remember that in low Earth orbit, your period of rotation is 90 minutes or so, 1.5 hours. So you always have to, I always have to pause and try to remember if the period goes as the 2/3 or the 3/2 power of the radius. You get basically this to the 2/3, and you find out that geosynchronous orbit is 6.3 solar radii. You rederive the density in terms of that. And did anyone else find, basically you need sort of a standard atmospheric or a solar wind density, sort of 6 particles per cubic centimeter in order to get the magnetopause moved inside geosync. Did other people get something similar to that? Sort of. I know there was like only one group maybe who did this, but some group did, I think.
We got slightly higher numbers.
Yeah. You know my tendency to not use calculators and doing.
Yeah, but we got like 55.
Yeah.
Oh, okay. All right.
Which is like a factor 10.
I kept this, there's this prefactor, which I think the text says you should use 2 and I use, or 1/2 or something like that. And I use these other numbers, 45 over 32 pi, because I like doing the image. Anyway, yeah, it's not an enormously large enhancement in density. And you will see in these big storms that the magnetopause can shrink in and leave these geosync satellites outside of the magnetosphere. There were a couple of other activities that were interesting. First of all, one of the exercises to go through if you're interested in Jupiter, it has a magnetic field strength that is 15 times the strength of the Earth. Okay, I mean, it's a big planet. It's got a very strong magnetic field, but it's only actually 15 times stronger than ours. So that would basically be 15 to the 1/3 power, which wouldn't be very much bigger. So you would think the Jovian magnetosphere is probably not too much bigger than the Earth's magnetosphere, just based on the magnetic field strength. Anyone know why that is not the whole story? This is a formula here. So this numerator has gone up by, well, 15 squared, but then I take the 1/6 power, so 15 to the 1/3 power.
The density will have fallen off. The density is like 25 times lower.
The ram pressure and the density and the ram pressure have fallen off by a factor of 25. That's right. So when you put in those numbers, you actually find out that the Jovian magnetosphere is 50 times the Jovian radius, not close to the, which is huge, which is essentially, you know, what is that? 5 times the radius of the sun. I think
so just a reminder that Jupiter is 5 AU from.
Oh yeah, sorry, right.
So the 25. Think about the solar wind lab and where the 25 factor of 25.
Right. Sorry, I think I had this in the lecture, but it's not here anymore. Right. You're at 5 AU. Jupiter's at 5 AU, and the density falls off as 1 over distance squared. So that's 1 over 25 or 0.0 and so that's where you get this enormous magnetosphere. And the last little exercise was what would happen if you took the current day Jupiter and moved it to 0.05 AU. That just happens. I don't think it was planned to be the perihelion of Parker Solar Probe. But if we had a Jupiter-sized planet orbiting at that distance, where would its magnetosphere be? Magnetopause. And I worked it out. I got 11 Jovian radii. So not that much. That's 5 times smaller than the current day. Did anyone get anything vastly different than that?
No, we got 10, so the same.
Yeah. Okay. Yeah. I mean, I thought it would just basically push the Jovian magnetosphere into the inside of Jupiter, but it doesn't. Yeah. The Mercury magnetosphere is something that kind of gets almost smushed into Mercury. We've had lectures on that, but that's a different topic entirely. And I think, yeah, so that's that. I think in the interest of time, we want to just end there. We can have questions related to this, but those were all the activities that we kind of decided to go over. So let me just leave you there, and I can answer any more questions as we take a break. And I think when we get back from break, Amitava is going to start telling us about the magnetosphere in reality. Amitava.
Good morning, good afternoon, good evening to everybody. It's great to return to talk to you again. Can you see my slides?
Yes.
Great. So I'm going to continue our discussion of Earth and planetary magnetospheres. I say continue because I see that Dana has introduced a lot of really neat stuff to you on magnetospheres already, and there will be some overlap, which isn't bad because when you're learning these things, some of these things bear repetition. But I'd also like to set it in broader context. I'd like to acknowledge my debt to Fran Bagenal, John Dorelli, Frank Toffoletto. There are lectures to the summer school. They have their lectures online, and I have liberally borrowed from them. And they in turn have also borrowed from the textbooks on heliophysics, the various volumes that Carol Shriver and George Sisko put together. This exercise of borrowing from each other's lectures is a reasonable thing to do. It also builds on the accomplishments of this school. And the lectures have gotten better and better because we have learned a lot from you in terms of what works and what doesn't work. So in a way, this all goes back to you. I'd also like to point out to you the new book on the horizon is Carol Shriver's Principles of Heliophysics. It doesn't have an exclusive chapter on magnetospheres, but does have very important magnetospheric physics discussed in chapters 4 to 6. You don't need to master all 3 chapters, but you will find important elements of what I am discussing here in each of these chapters. With that said, let me start with the advent of magnetospheric physics. And since Dana is taking a little time, I might as well begin with a story. The story of the discovery of the Earth's magnetosphere going back to 1958 with this remarkable historic picture of Van Allen in the middle, flanked by Pickering and von Braun, who were scientists and engineers who helped him. And in fact, the triumphs of space physics has been this great partnership between science and good engineering. evident in our history from its very inception. I'd like to share with you some stories of Van Allen. When I was teaching in Iowa many years ago, and it was under rather tragic circumstances that I was actually recruited as a faculty member at Iowa, because there was this terrible incident of a graduate student who actually killed 3 professors on his dissertation committee, and I was a replacement for one of those 3. And Van Allen played a singular role in recruiting me to work with him. My office was 2 offices down from him. He had already retired, but was still a very important influence in everything at the University of Iowa. And he did tell me that he began his life as a plasma physicist in fusion, where I am spending a lot of my time now. And he was, in fact, Lyman Spitzer's postdoctoral fellow, one of his first. Lyman Spitzer, who was a great astrophysicist, was also one who started the Princeton Plasma Physics Laboratory and the fusion program. And Van Allen was his first experimental postdoc who took one of his clever ideas on a fusion device and did an electron gun experiment. So Van tells me, or told me, unfortunately he's passed away now, but told me that Spitzer was a great person to work with, but he and Spitzer differed in one very important respect. Spitzer thought back in the 1950s that they would solve the fusion problem in 5 years, and he had underestimated how hard the problem was. It was probably one of the few things that Spitzer was a little wrong about, because he was right so much of his life. And that is not because he was given to magical thinking, but because I really think that plasma instabilities and how insidious they are was not known at the time. And so in the confluence of space and fusion physics, plasma physics grew as a discipline. So Van told me once that the only difference that he had with Spitzer was that he decided after 2 years that this problem was not going to be solved in 5 years. So he decided to go back to Iowa, his home ground, and decided to fly rockets and balloons. And now we have space physics, thanks to Van Allen's defection from fusion physics and a whole discipline. So much of space physics really began with magnetospheric physics in the sense we know it today. Of course, a lot of the things on the sun have been historical, as many of you know. You picked it up from other lectures. But magnetospheric physics as we know it today can be traced back to this pioneering mission where they discovered the Earth's radiation belts. And now the picture is a lot more complete thanks to many missions that have now gone around and mapped the Earth's magnetosphere with ionosphere and below to a surprising degree of accuracy. I say surprising because if you look at this space-time continuum of outer space, you would still think that we are severely undersampled. But we know a lot more about the magnetosphere than we do about even the sun in some ways, and certainly a lot more than astrophysical objects. And so the various components you see, many of which you have encountered already, the sun is to the left, the solar wind coming in. Here is beautiful Earth, and here is the magnetosphere around it. The Earth's atmosphere extends up to about 100 kilometers. Between 70 kilometers and above, you have the ionosphere, which is a source of wonderful physics, both for instabilities and turbulence. You have incoming solar wind particles. Only about 10% of what the solar wind hits the magnetosphere with eventually finds its way into the magnetosphere, but it does. That's why we have plasmas within. You have the Van Allen radiation belts. And I'll talk more about that in a moment. Here is on the left, the day side of the Earth's magnetosphere with the bow shock and the magnetopause intervening, filled in between by the plasma that occupies the magneto sheath. Most of the solar wind particles are deflected. Some of it, because of reconnection and other things, finds a way to populate the night side of the Earth's magnetosphere, where you have the plasma sheet and the neutral sheet that lies embedded within the plasma sheet, where the magnetic field lines change direction, the source of what are known as magnetospheric substorms. In fact, this entire distance terminating here with field lines on the ionosphere, but extending on the right side to very far distances, well in excess of hundreds of Earth radii, is what constitutes the magnetotail. So this is a quick qualitative overview of what the magnetosphere looks like. And before I get further into a discussion of the radiation belts or the ring currents, I promised Professor Knipp that I'm actually going to do a few things in single particle orbit theory in order to set up her lecture and mine as well. So a few things from single particle orbit theory that I expect you know, but perhaps is worth a quick review. This is the Lorentz law, left-hand side, non-relativistic equation of motion. mdv dt. On the right-hand side, you have the force, which is the charged particle times electric, and the Lorentz force. And a lot of the motion of charged particles is very useful to think about in terms of the guiding center, which in this particular simple case lies smackly on the magnetic field. The particles are gyrating around the magnetic field. The guiding center is a fictitious object designating the center of the cyclotron orbit, but it is not where the particle truly is. The particle is a Larmor radius away, designated here by rho c. The magnetic field is along y, the motion is along x and z. So if you consider as a special case, where you have a constant electric field and a constant magnetic field, it can be shown by rigorous substitution in this equation that if you write this as mdv parallel dt, then this term makes no contribution and this equation simply becomes parallel to the magnetic field. This term drops out. mdv parallel dt equals qe parallel. That then gives you, or gives the guiding center, a parallel acceleration given by the parallel component of the electric field. But if you write the same equation in terms of perpendicular, what you will have is mdv perp dt equals qe perp plus v perp cross b. And if you invert that equation exactly, you get the famous E cross B drift of particles, all particles drifting with this velocity in a direction perpendicular to E and B. So here's my first question to you. And this is where we will go to the mode. I don't know whether Dana is back, but Nick is minding it. Consider a steady time independent electric field. So curl E is 0. So you can write E as the gradient of a phi, where phi, excuse the missing typo, is the electrostatic potential. All charged particles drift on, and you have a choice of three answers. Equipotential surfaces, perpendicular to equipotential surfaces, neither A nor B. So I'll give you 30 seconds to answer back, and then we'll do this in the way in which we have done it before. Raise hands.
Yeah, and we should do a raise hands if you have an answer.
Ready?
Okay, we had a few hands go up and then disappear. So Joe is the hand that's gone up most recently and stayed up. So maybe he wants
Joe.
Yeah, I would think it would be B, because if you think of the Lorentz force, it would accelerate in the direction of the electric field rather than perpendicular to it, because it's E plus V cross B, or negative E plus V cross B. So it would follow the electric field rather than following the equipotential surfaces. Now, when it comes to the magnetic field, it follows the equipotential surfaces of the magnetic field as it drifts, but not the electric field.
Okay, so Joe's answer is B. Any other takers?
Deb also has a hand up and remained up. Oh no, I think it went down. So that's it.
Deb? Oh, okay. So
No,
Dana, you said this.
yeah, it's a kind of B answer.
Oh, okay.
Same kind of, yeah.
Okay, so there have been few answers and the answer is B. But actually the correct answer is A. And let me explain to you why. E cross B is in a direction perpendicular to both E and B, right? So that's the drift you see. So if there is an E field pointing this way and B field pointing this way, then the direction of the E cross B is perpendicular to both E and B. Now, what is an equipotential surface? An equipotential surface by definition is one which is normal to E, right? Because if it were not, suppose if E were not normal to the equipotential surface, but were inclined to it at an angle, then there will be a component of E parallel to the surface. But if there is a component of E parallel to the surface, then it would not be an equipotential surface, because equipotential by definition means that phi is actually constant. There can be no gradient of phi on an equipotential surface. So E is always normal to equipotential surfaces. So if E cross B drift is perpendicular to E and B, and E is perpendicular itself to the equipotential surface, it follows that drifting particles all lie on surfaces of equal potential. So actually Joe was thinking right. The only part where he missed the beat a bit is because he did say correctly that the electric field would determine what the primary direction of E cross B drift. The thing that he missed was that the electric field is always perpendicular to an equipotential surface, and the E cross B drift is always perpendicular to E. Therefore, the E cross B drift must lie along equipotential surfaces. Good? I wish you could say yes. Joe?
Yes, yeah, thank you. Yeah, I totally forgot about the E cross B drift thing, which is funny because I'm actually writing a paper about that right now.
Good, timely reminder then. These things happen all the time. I was just testing whether you guys are awake or not. We're throwing so much information at you, and this has been a long week, but this is just a way. Okay, but thank you for answering. It doesn't matter that one is wrong once in a while. It's just have to reason your way through this. That's one type of drift, which is an exact drift. There are two other drifts I want to talk to you about, which are not exact drifts in the following sense. That particular answer was exact if E was constant and B was constant in space and time. But most magnetic fields in nature are not constants in space if they are constants in time. Let's forget about time dependence at the moment, but at least let's assume that the magnetic field has spatial gradient in the manner in which you see here, where there's a magnetic field perpendicular to the plane of the paper with the arrow pointing upward. And as you move to the right, there is a gradient. So the magnetic field is actually getting stronger. So pictorially imagine a charged particle coming in and trying to wind its way around in a cyclotron orbit. But while it does so, it's not seeing a constant magnetic field, but a gradually increasing magnetic field to the right. So the cyclotron orbit actually has a larger radius on the left than to the right. So the particle actually ends up not completing a tighter, a less tight circle, but gets wound around and is now going up and winds around another circle. And notice, because of this, in a certain amount of time, the guiding center of the particle's orbit is actually drifting along a direction perpendicular to the gradient of B. And using approximate equations of motion, by which I mean one cannot solve this problem exactly, except because in inhomogeneous magnetic field problem, without making the assumption that the Larmor radius of the particle is a small fraction of the scale length of inhomogeneity of the magnetic field. In other words, if gradient B you think of as B over L, rho C over L is assumed to be a very small number. Under those conditions, what you get is an additional drift, which is called the B cross grad B drift, or otherwise simply known as the grad B drift, which is perpendicular to both B and grad B. So in this particular case, B is out of the plane of the paper, grad B is to the right, so B cross grad B lies upward, exactly as you see here for the positively charged particle. I said positively charged particle because if you had a negatively charged particle, it will gyrate the opposite way and the drift would go the other direction. So this actually, unlike the E cross B drift, which is not dependent on charge or mass of the particle, is actually one that is dependent on both charge or mass. W perp is actually the perpendicular kinetic energy. So that's the B cross grad B drift. Very important drift to keep in mind for the Earth's magnetosphere. And essentially, you can intuit this result by replacing QE in the E cross B derivation by an effective gravitational force, if you will, call it mg, where G is some fictitious thing, not real gravity, which is much smaller influence on these particles than the magnetic forces. And what you have is E essentially replaced by an effective gravity type of force, which depends on both charge and mass. There's another drift, which is called the curvature drift, which is when you're going along a curved magnetic field line, you feel there's like a centrifugal force in the reference frame of the particle. And that can be written as 2W parallel QB square radius curvature cross B over RC square, where RC is the radius curvature of the magnetic field. This too is actually a charge and mass dependent drift. These are the curvature and grad B drift and E cross B drift are the three most important drifts that you need to keep in mind in order to understand things like the ring current in the Earth's magnetosphere, which I'll come to in just a moment. But before that, in order to understand Van Allen radiation belts, I would like to also get to adiabatic invariance. But as I just said, the ring current in Earth's magnetosphere, here's an example. So here's a North Pole and here's a South Pole, if you will. And you have magnetic field. As you know, the magnetic north and the magnetic south are actually exactly opposite of the geographic north and the geographic south. And this is your dipolar magnetic field structure. So this dipolar magnetic field structure has both gradient as well as curvature in it. Gradient because as you go out from the Earth towards longer and longer distances, the dipole field falls off as 1 over r cubed. That's your spatial dependency. But it also has curvature It obviously does, because the dipole magnetic fields are curved. So it's a vacuum field. So if you can show by a few steps in algebra that actually the gradient B drift and the curvature drift simply add vectorially. If you use the property that curl B equal to 0, and you essentially get one number. They're equal to each other, and they're one number, just twice the value. So that's what the particles are left with. Since it's a charge-dependent drift, it turns out that the electrons drift in this direction and the ions drift in the other direction. That's essentially the basic physics of the ring current that goes around. In Professor Knipp's lecture, I'm sure she'll be devoting a significant amount of time on geomagnetic storms, which actually perturb the ring current in very non-trivial ways. So when it comes to space weather, how this ring current is treated and what effects the storm has on it are subjects of great interest. This is the polar view. This is the oblique view. Okay. So that was
we have a question from Jeff.
Yes, Jeff, please.
Hi, I'm just trying to make sure I understand this correctly because I'm getting a little bit confused with the gradient drift. Okay. I know that the geomagnetic field will get stronger as you get closer to towards Earth, but also it gets stronger towards the poles. So is there a way to break down this gradient drift, I guess, in both components?
Aha. So I hear what you say. At the ring current level, where it is, that you're right, that it gets more intense near the pole. And what you're getting is that these field lines are curving down, as you say, and instead of developing a gradient B. But that effect is much more local in the ionosphere than its effect on the ring current. For the ring current, the dominant gradient B that affects is the gradient B that you see here.
Is it a difference? Is it a different situation if we're not necessarily speaking to the ring current?
That's correct.
Okay.
Depending on which area of the magnetism, for example, if you were to ask me about the particle drifts in the ionosphere itself, the intensification effect that you talk about is going to be much more important there.
Okay.
And what is very interesting, since you mentioned this classic statement we make that the E cross B drift doesn't separate charges, is not true in the ionosphere. And you know why? Because there are collisions. The ionospheric plasma tends to be a lot more collisional than the plasma out there in the area of the ring current. And so even E cross B drifts in the ionosphere produces a charge separation in a way that the simple explanation I gave you doesn't fully account for.
Okay, thank you.
You're welcome.
Can I ask a follow-up question?
Please.
Yeah, so what I want to say is it correct to say that near the poles, this particular hybrid drift gives way? I mean, the curvature drift goes out and the drift is mostly a gradient drift for electrons near the poles?
The electron, so there is another thing that complicates a lot the description of the particle trajectories near the ionosphere because of the existence of strong parallel electric fields. In those cases, locally, you actually have models which take the ionospheric magnetic field as non-uniform and where you can understand a lot of the particle motion from the presence of intense electric fields that occur there.
Yeah, I mean, the curve would be very near to zero, right, near the poles.
Correct.
The curvature.
Correct.
That's why I was wondering.
No, you're right about that. You're right about that.
Thank you.
Okay. There's an excellent book by Michael Kelly, which is called The Ionosphere, which has a very good discussion of what all the drifts are in the ionosphere and where they're relevant. And I strongly recommend a side reading to look at that for those of you who would like to follow up. I made some quick reference to the ring current, and now I want to talk about the notion of adiabatic invariance. This actually goes back in a way to Solvay Conference 1911 of Albert Einstein. And of course, the idea of Hamiltonian mechanics and constants of the motion are well known in the classical physics literature for a couple of centuries. But the idea of an adiabatic invariant is actually somewhat newer compared with that. It's still pretty old. And Einstein was asked this question, that suppose if you have a simple pendulum that is hanging, and imagine this pendulum is going through some simple harmonic motion back and forth. So he was asked about how this would change if somebody just pulled up the pendulum ever so slowly. So if you pull up the pendulum ever so slowly, since the period of the pendulum does depend on the length of the pendulum, it's quite clear that the time period or the frequency of oscillation is going to go through a change. Similarly, the energy would also go through a change, because energy is simply the kinetic energy plus the potential energy. The kinetic energy has also a term that goes like half omega square L square, where L is the length of the pendulum, and omega depends, of course, on the length of the pendulum too. So both energy and time period would actually change, but Einstein, upon being asked a question, immediately responded that he thought the ratio of energy to the frequency would remain approximately invariant. This is actually very consistent with principles of quantum mechanics too. For those of you who know the history of quantum mechanics, Planck had suggested at the time that the energy of photons and energy and their frequency is related by a simple relation called E equals h nu, where h is the Planck's constant. And a lot of people did model at the time thinking of electrons as quantum harmonic oscillators. And he hinted that, not that, but h is an universal constant, so you have to be careful about that. Einstein was actually saying things will change, but it will remain approximately constant. But what approximately meant had to be settled a long time later. And so the situation mathematically that one is looking at is a harmonic oscillator. And you've done this in freshman physics, which is d2x dt squared plus omega square x is a constant. And imagine that it had no time dependence. Then you know exactly how the harmonic oscillator works when omega is actually constant. But if you actually do make the spring constant a slightly changing function of time, in effect, the person standing on the platform pulling up the pendulum ever so slowly is doing just that, then one can show that this invariant that Einstein was referring to in simple one dimensions can be written as what is called the action integral, which is the area under the curve of the motion of the particle PdQ taken over the whole orbit. When the harmonic oscillator or the pendulum is going back and forth in a periodic orbit with a certain amplitude A, then you can define in PQ space an ellipse where the particle is undergoing adiabatic motion. And it was later on shown by Kruskal, Martin Kruskal, who is a plasma physicist, but more than that, a mathematical physicist who actually had a major hand in discovering solitons as well. One of my teachers when I was in graduate school, I'm pretty ancient as you can tell, a long time ago. And he actually proved this relation to mathematically, that the change in the adiabatic invariant would go like an exponential minus some constant c of the order unity divided by epsilon. Now, those of you who have a feel for exponential functions know what the property of this is, but I have a question for you. So in short, yes, if epsilon is very small, then you have something that is like an approximate constant, but approximate it is because it varies depending on how small epsilon is. So I have a question for you. Adiabatic invariant is A, an exact constant of the motion, approximate constant of the motion which decays as a power law in time, or approximate constant of the motion which decays slower than any power law in time. I'm just trying to make things more quantitative. Do you want to give it a shot? Just a qualitative answer? Are you guys staying up with me? Keeping up with me? I can't see the screen. How are we doing, Dana?
Doing all right. Gwen is offering an answer.
Terrific. Any more?
Satabwa? Satabwa?
Satabda.
Okay, thank you.
These Bengali names pose a real challenge, I know.
Mm-hmm. That's what we've got so far, as far as hands.
Hey guys, last time I thought there was a lot more responses. Are you getting tired of me?
Now, Joe.
Okay, let's go with Gwen.
I think it's C. I mean, I'm pretty sure it's not an exact constant of the motion, and I think it decays slowly. I'm not 100% sure about slower or faster than like any power law.
Yeah.
But I think it's slow.
Yep. Any more answers?
Well,
I agree with Gwen.
I thought it can be A, and that the constant will change with different ellipses. Because the area of the ellipse will become time dependent.
Okay. So certainly A is ruled out, and all of you are right about that. Turns out that Gwen is actually right, because the exponential function beats out any other slower form of decay because it's the most rapidly going. And my naive way of describing it is that, you know, any exponential power series has powers going up to infinite power, right? And it actually sums up very neatly to an exponential. So we are very lucky about. This is one of those beautiful mathematical results that you add an infinite number of terms, which you get a finite result. But since it has an infinite number of terms, anything that you can come up with a power law in time will always be beaten by some other higher order power, no matter what the exponent is, because the series doesn't terminate. If it did, it would be a power law and not an exponential. So the answer is that this is very good. Now, this is not just a mathematical issue. It has enormous physical consequences. Because what it means is that imagine these charged particles that go around. Here is what I would call a mirror machine or a mirror plasma. You have magnetic field lines. And so imagine you're looking at the Earth's dipole field, but you have taken it off the ionosphere end and you've straightened it out just for simplicity. By the way, this is also a very important fusion concept, the mirror plasma, which is no longer one of the most pursued ideas, but very interesting physics. So you have strong magnetic field in these throats and particles can go back and forth. You have cyclotron motion, which is the most rapid. You have parallel motion as well. You have drift, gradient and curvature drift. This is the kind of thing that gave you the ring current. And so there are three types of bounce motions. The parallel motion, because if the velocity of the particle, parallel velocity is not large enough, the particle will be confined between the throats of the mirror and have this sort of a gradient and curvature drift at the same time. And why what you just discussed is a matter of great importance is because if the adiabatic invariant were just good for one or two oscillations or gyro motion cycles of the charged particles, these charged particles won't be confined for very long. When they actually have the potential to be confined in the radiation belts for a much longer period of time. And for the 3 types of bounce motion, you actually have the first adiabatic invariant, which is mu, which is the ratio of the perpendicular energy to the magnetic field. You also have the second adiabatic invariant, which is the parallel motion going back and forth in a confined bounced orbit. And then the third adiabatic invariant, which is the magnetic field going through and pi r square, which gives you the flux threading the ribbon. So you're looking at phi going through this ribbon. And by the way, as you know, if I move this circle up and down, B and R square are going to be such as to keep the same flux in it. So you've got two motions associated with the cyclotron and the gradient and curvature drift. That's mu, that's phi, and J corresponds to the parallel motion. In fact, for those of you who remember the shock acceleration picture of Fermi's that we were talking about in my earlier lecture, the conservation of J was an important reason why when Fermi moved his mirror, and if they moved inward slowly, parallel energy would go up, which we associated with first order Fermi acceleration. Now to go on and why this is important, of course you know about the ring current, and I have to put it in context, the drift of electrons and drift of ions are in opposite directions. So that gives you the ring current. But now I'm looking at a Van Allen radiation belt possibility here and how we might have these. And I'm going to talk about that in just a moment and what we have learned very recently from it from Van Allen probes. But let's look at a dipolar magnetic field line. And as you all know, just as was pointed out in my earlier talk, is that there are going to be regions where the magnetic field line is going to be very strong near the throats. And you'll have gyro motion, you'll have parallel motion, and you will also have an overall drift motion such as of the kind. Now, if you look at the time scales of each one of them, they're very well separated in time. The gyro motion occurs typically in time scale of milliseconds. So that's the fastest. The bounce motion, as I just mentioned a little time ago, is a somewhat slower one, 0.1 to 1 second typically. And the drift takes much longer, 1 to 10 minutes. Now, as long as the field that is guiding the particles change slowly in time and space compared to the characteristic motions, these invariants are very good. And in fact, it is at the heart of why it is that we have the radiation belts. And the classic picture of radiation belts is that there is an outer Van Allen belt that you see here. And then there is an inner radiation belt separated by slot regions between these where no such belt particles exist. Those are not the only trapped particles. You can have interstellar matter that is actually trapped. You can have energetic ions that are trapped. But the Van Allen radiation belts are the ones in which you have electrons and protons that are actually trapped, that are fairly permanent features of charged particles that are in the Earth's magnetosphere. The radiation belt storm probe, which came to be known as Van Allen probes, actually found something pretty remarkable. In addition to these two well-known belts, the inner radiation belt and the outer, it actually found a third radiation belt using the electron-proton telescope on board. And this is an unusual radiation belt configuration that consists of now 3 belts and 2 slot regions. As to how this third belt forms, and it is not always present, is a subject of considerable research. There are interesting ideas out there, but none very definitive yet, that allows us to pin down exactly why and when these third belt forms and what makes its lifetime, when it is seen and not seen, and so on and so forth. I won't dwell on this subject any longer because it will take me off the mainstream of this lecture, but it was good for you to know that thanks to Van Allen radiation probe, or RBSP, we now have deeper understanding of belts. We also have very interesting information on what accelerates particles in these belts. One of the things that I should point out was that the adiabatic invariants are by no means completely sacrosanct objects. As you know, they really depend on 3 types of periodic frequencies. So if there are waves that actually break the adiabatic invariance, then you actually can see significant acceleration and heating of the particles in the radiation belt. Example, you might recall from my lecture on particle acceleration, I talked to you about the importance of the ion cyclotron waves. These ion cyclotron waves, when they obey a resonance condition, they actually are producing frequencies which are comparable to the cyclotron frequency, because they are based on a resonance condition between the wave and the cyclotron frequency of the particles. That, for example, is a condition under which the adiabatic invariant mu would break down. Because of the very disparate timescales, there are different types of waves that you would need in order to have resonances with either the gyro frequency, the bounce frequency, or the drift frequency. And you go from the fastest wave to slower ones. But through the phenomenon of resonance, you can break the adiabatic invariance and you can detrap particles. You can also accelerate them locally. And these are subjects of very intense research. The other thing that can also break adiabatic invariance is collisions. Remember, all this stuff that we are talking about assumes that the particle is able to complete these periodic motions without colliding with another or colliding off a turbulent background and be scattered out. The turbulent background can in fact be made up of waves, as I just indicated. So the Earth's magnetosphere has a very complex current system, probably the best understood of all magnetospheres. And what you see here are the entire family of currents that actually are present in the Earth's magnetosphere. You have, in fact, the so-called cross-tail currents that are out of the plane of the paper, if you will. The magnetotail is lying in this 2D cross-section of the tail. There are field-aligned currents that go from the ionosphere, connect to the magnetosphere. These are disrupted strongly when you have storms of the kind that you will hear in a later lecture. You have the ring current that we just talked about. We have, trying to look at what else haven't I mentioned. What I haven't mentioned here is the dayside magnetopause current, which in fact goes into a discussion of how our magnetopause actually forms. You already heard quite a bit about that in Dana's lecture, but I will be discussing right after this what's going on in the Earth's magnetopause.
So Amitava, sometime in the next maybe 5 minutes, we could take a break, or whenever it makes sense, but.
Sure.
Almost.
Maybe go just another 5 minutes?
No, yeah,
take a break?
sometime, whenever it makes sense.
Sure, any questions? Are you guys keeping up with me?
I have a question regarding the slot regions. So why do they form, or why at certain heights?
I was hoping you would ask the question and hoping you wouldn't ask the question. Thank you for asking it. You know, I cannot tell you that there is a good theory for why the slot region actually exists. There are a bunch of ideas out there that there are instabilities that are triggered in that region, both micro, describable by kinetic theory, which can be coupled to longer wavelength instabilities that destroy that destroy any possible formation of the belt, though really depend on local plasma parameters. But if you just look at the picture as I have it, this does not make clear at all why there is a slot region at all. Because you can well say, well, the drifts that you're talking about are all there. Why isn't there a plasma there? And why don't we have a belt? I cannot give an answer to this question to you that will be anywhere close to satisfactory other than what I just said. There are people maybe who are radiation belt experts, and maybe somebody else in the audience knows more precise answers to this question than I do. Is Dolores on the call?
I am on the call, Amitava. There are, as you mentioned, many ideas, and one of them has to do with the frequent lightning that is seen at mid-latitudes and the waves that are generated by that lightning that can make their way out into the magnetosphere and result in a kind of a precipitation or clearing out. So that's one thing that is under consideration. So it would actually be a control from Earth's atmosphere. And you'll notice that those belts very conveniently, that slot region rather conveniently maps to mid-latitude regions. So that's one thought. And then Dan Baker has also indicated that there are a number of radio transmitters that have been operating just right around the time of World War II and ever since, that also generate waves that may cause the invariance to be broken. So just lots of ideas, and it may be multiple things that have ways that can be tested. Dan has suggested that the Navy turn off its radio transmitters and see if you could repopulate that region, but we don't think that'll happen.
Okay, thank you, Dolores. Those comments really help. And it basically gets down to outside of the domain of single particle orbit theory in the manner in which I indicated. And therefore, wave particle interactions, if you want to call it a broad category of possibilities, have what has been discussed, either triggered by lightning, as Dolores pointed out, or other related things, but no convincing or unique explanation that everybody embraces. Let me move on to the Chapman-Ferraro magnetosphere. I noticed that in the activities that Dana did with you, he covered this quite a lot. And so I am glad in a way, and so I can go through this a little bit faster and hope that you will actually stop me if you have questions. And the whole Chapman-Ferraro magnetosphere was a very major conceptual breakthrough, and it was taken from this classic paper of Chapman and Ferraro trying to give a theory of magnetic storms. But while they were going about it, you have to remember at that point, we didn't know very much about the magnetosphere, which is what makes their accomplishment all the more striking, a real leap of insight. For example, we didn't even know that there was a magnetotail at that point. It came a lot later. But the problem they posed was, well, there is solar wind. And imagine a very simple geometric model where you have magnetic fields on one side and you have solar wind flowing on the other. And would there be a surface across which there will be no flow penetrating and no magnetic field outside? That was the way they posed the problem. And that was, in fact, the Chapman-Ferraro problem. But now I have a question for you. The energy of the solar wind has three components: thermal, magnetic, and flow. Which is the largest energy density? A, B, or C? And knowing all that you now know, I know many of you guys will know this answer almost instantly, but let me ask it in any case.
So Laura was quick with an answer. And also Gwen may have had a question before that. The hand is.
Okay. Oh, okay.
Yeah.
Yeah,
But
so
my
it's
question
flow.
is like,
Sorry.
Oh,
Go
sorry.
ahead, Gwen.
I should
Go
organize.
ahead, Gwen.
Let's have Gwen's question first, and then Laura can give us the
Sure.
answer.
sure, sorry. My question was like from a few slides ago, you had shown like a trapped population from interstellar plasma?
Yes.
Is that like there's really like a place in Earth's magnetosphere where interstellar matter is hanging around?
Cosmic rays.
Okay. And they just all hang out in that one like
In that one, yeah.
magnetic latitude?
Yes, yes.
Weird.
That's interesting, isn't it? That we have astrophysical sources. And if you go out to the outer boundary of the heliosphere, as you know, we have missions flying there. IBEX, which went, and IMAP now that is expected to fly. We are not isolated from the outer universe by any means. And because we focus so much on Helios, we don't spend a lot of time thinking about it, but ISM does have presence within the magnetosphere.
Why doesn't it just mix in?
Why doesn't it mix in? Well, that's a really good question. I'm not so sure that it doesn't mix in, because you definitely have traces of interstellar particles in the Earth's magnetosphere. These are not very high percentages, but nonetheless there. And as to why they don't break up and mix in, it's the same kind of a thing as we have for the radiation belts. You have pretty tight invariants of these things controlling them so that they do in fact form such a belt. And then the question is, what will break the invariants and have them mix in? And undoubtedly, like other major geomagnetic disturbances can cause particles to escape and be assimilated in the broader magnetosphere. So can they be, but then they can be repopulated again. Does that make sense?
Yeah, that helps. Thanks.
Sure. Now to the question very quickly.
Yeah, Laura is a.
Laura, go ahead.
Yes. So it's the flow.
Oh, yes, Laura, you have it. And I'm sure many of your friends think the same. Before you go on a break, I just wanted to give you some numbers on why that is so and give you comparison of the things. These are numbers that are taken from ambient parameters of the solar wind. So half rho v square for the solar wind. These are densities that we are looking at. 400 kilometers per second was the number that Dana was using. You get this as the energy. And if you look at the magnetic field energy with b squared over 8 pi, it comes to 1/50th of the flow energy. If you look at the thermal energy, that's about the same order. So the flow energy is by far so much greater than the pressure or magnetic field energy. The Mach number, the alphenic Mach number is about 7. And the Mach number with respect to the speed of sound, 5/3 is gamma, is about 8. So both Mach numbers, interestingly enough, are comparable in the solar wind. And that's primarily because the plasma beta of the solar wind is typically of the ordered unity. These numbers need not be the same. For example, going out at coronal distances, these are different numbers if beta is much smaller than 1. So basically the physics says that the flow controls the magnetic field and drags it along. The magnetic field is essentially frozen to the plasma. So let's take a break here. Let's keep it at 5 minutes. I have a long distance to go. So let's have you back relatively soon. Thank you.
Thank you, Amitava. It's great preparation for tomorrow's lecture. I'm actually going to remove a couple of things and put something else in, since you've covered some things so nicely.
Well, thank you, Dolores. I had you in mind and I had made a promise. Maybe I went into it even more than I needed to. But...
Oh no, I think this is fine. I will be talking, because there's such a zoo of storms, I will not be going into great equation depth, but just trying to get things sorted out. But so the students really need this background to have this qualitative discussion make sense.
That's great. Good to hear. Maybe people are also getting a little tired, huh?
And you can take us into the magnetosphere.
Good, thank you. So I'm going to talk to you about Chapman-Ferraro's work on the magnetopause, bow shocks, and so on and so forth. And it's really important to realize that conceptually, they really did make breakthroughs, even though they started with the simplest models that they could. And it's always the great way to do physics is to come up with a simple enough problem that gives you a really interesting answer without building in all the complexity. And the ability to do that is, as you know, is a pretty remarkable ability. So the way they posed the problem is to say, find the surface that confines the Earth's magnetic field and excludes the solar wind. They thought, therefore, that to leading order, what we talk about the magnetosphere being the Earth's magnetic shield, without which life would have obliterated. And by the way, this is one thing that you should all keep in mind as we go forward, is that there is a tremendous amount of interest now in exoplanet. And there is exoplanet habitability, which is a subject of great interest. But looking for life in exoplanets has usually begun from the premise that we look for moisture first. Now that's in fact a necessary condition, but not a sufficient condition for life. If heliophysics and the Earth's magnetosphere has taught us anything. If you had the equivalent of something like a Carrington event of the kind that Dolores Knipp will talk to you about tomorrow, then despite all the moisture, if you had a sufficiently violent event that wiped out your magnetic shield or wiped out your atmosphere, and this has been known to happen for comets or other objects in the heliophysical system, then life is gone. And one of the things that exoplanet people have to recognize is that heliophysicists know a lot about the effect of major storms that can evaporate atmospheres. And there are examples like TRAPPIST out in the outer reaches of the universe, where people have actually recognized that these are exoplanets in the vicinity of a sun or a star, which is sun-like in many ways. But the distance that separates such exoplanets from the star around which it is orbiting are often much smaller than the distance that separates Earth and sun. Now, we managed to have survived a Carrington event, but the exoplanet life may not. A Carrington-like event might completely evaporate atmospheres. So I don't want to digress too much, but the questions that we are posing here, I believe when more and more observations become available, would be really burning questions for the whole question of habitability in all these multiple planets that we are discovering. But returning to Chapman and Ferraro, their thing was, let me take a sharp boundary on which I'll prescribe currents. There will be vacuum magnetic fields on the left-hand side, no solar wind. On the right-hand side, there is solar wind and no magnetic field. So we impose the boundary condition that the component of B normal to the predefined surface vanishes. Well, across that, you have force balance. But as you just pointed out through your answer, to leading order, the primary component of that pressure is really the solar wind pressure rho s vs squared. On the left-hand side, you have the magnetic field. So to leading order, if you balance this is the Chapman-Ferraro problem given a certain bounding surface. So how do you compute the shape of the magnetopause? They made a very simplifying assumption that in fact it's like a specular reflection. So by the way, I am not saying that energy has direction. Don't misunderstand me. It's momentum which has direction. And that momentum will in fact have a 2 rho v SW cos theta component perpendicular. And if you square that and take half of that, you get factor of 2 here. And this is how you get the balance between the magnetic field pressure and this to leading order, with B normal being 0 on this surface, which is your defining surface. So what people actually do, as Midgley and Davis did, and others have as well, is to solve by brute force a problem. Specify that the magnetic field vanishes outside a boundary surface S. Parameterize that surface. In fact, Midgley and Davis took 37 independent parameters. The pressure balance relates the surface current. There's current on this surface, but none inside or none outside. And then you do a spherical harmonic expansion of surface current with coefficients. Again, a very high dimensional parameter space, so as to cancel any remnants of the dipole field outside of the surface. By so doing, they implement actually the Chapman-Ferraro program, where you actually have a curved magnetospheric, a curved boundary where Bn is 0, where there is current that resides it. Inside is dipole fields. Outside there is no field, only the solar wind. What they came up with was a picture that Dana has already shown you. And in fact, it was implemented by others as well, but it's not a very good realistic model of the deflection of the solar wind around the magnetosphere. This is where you have a fudge constant, if you will. They had assumed that K was 2. And the basic idea is specular reflection is highly idealized. The number turns out to be more of the order of 0.881. Nonetheless, this model has enormous, I mean, the part of K is, of course, you see we don't quite get it right. We're off by a factor of 2, but that's not bad at all for a qualitative model. And that's why when we're having this question and answer the other day, when Dana commented that if you do Chapman-Ferraro, you get a magnetopause distance that isn't bad, really isn't. And if you look at what happened there historically, that the energy of the solar wind, it was realized, is dominated by the flow. And the theoretical way to deal with this is to treat the flow as gas dynamic and to a first approximation neglect the magnetic field. Back in the 1960s, that's exactly what Spreiter and other people did. And this code had been developed for weapons applications actually to treat the flow around missiles. But Spreiter very quickly modified it to address this problem, assumed that there was an axially symmetric shape for the magnetopause. And since the solar wind is supersonic, it forms a shock as it enters the Earth's magnetosphere and slows down, exactly as Dana was talking to you about. And if you look at the collision mean free path of the solar wind, it's of the order of 1 million Earth radii. It's a very highly collisionless system. Whereas the thickness of the bow shock is of the order of 1,000 kilometers, which is more like an iron gyro radius. More on the thickness of the bow shock and what physics goes into that a little later. As you can see that doing this is in itself an indicator that we need to start thinking about what happens in this 1,000 kilometer radius and what physics matters. And I'll get to that very quickly. But if you actually proceed with the Chapman-Ferraro program implemented, say, in a Spreiter kind of a setup where you run codes and stuff like that, you recall this formula that you and I talked about where, by the way, here M infinity doesn't mean that the Mach number is infinity. It really means what the Mach number is at infinite distance away. But if you go to the limit of a very, very high Mach number shock, then you got this compression ratio to be 4, you remember. And that's the number, that's what this formula is. Now, if you use this, you find that delta over D, which is the distance from the bow shock to the magnetopause, is 1.1 rho infinity by rho 1. remember the Chapman-Ferraro theory or Chapman-Ferraro-like models are models derived under strict approximations. Nonetheless, it's amazing how good they are. This happens to break down when the upstream Mach number approaches 1. And so that's not bad at all for the fact that when you get large Mach number limit, you still have a number that's still pretty good. And there's a pressure pileup. Pressure must increase as we approach the subsolar magnetopause. The subsolar point is this point here. And this is where the solar wind gets diverted. So much we know, and I'm going through this in a somewhat faster way because you guys already know more, if not entirely by yourself, but also because you attended this summer school. The question is what happens when we include the magnetic field. Fortunately, we have global codes that done that, and I had the privilege to work with John Dorelli, who was actually a young researcher at the University of New Hampshire when I was teaching there, and we collaborated on a bunch of papers to do with the magnetopause. And he was in fact running global general circulation model, the open GGCM code, which was developed by Jimmy Rader. There are few other codes that are similar and are very good codes, provided you give them the resistive MHD equations, which is not a very good approximation for the collisionless magnetotail, but a good place to begin. And what you find, in fact, is that the magnetic energy actually increases, whereas pressure and density decrease. And this actually caused some significant variations in the predictions of Chapman-Ferraro or gas dynamics prediction. And the problem with the gas dynamics predictions is that as you go and approach the magnetopause limit and you go to the zero magnetic field limit, they tend to have singularities. Now, I want to take a pause and tell you that I just referred to as that magnetopause boundary, as having a very narrow thickness, about 1,000 kilometers. And there are configurations of magnetic fields. If you look at the magnetic field, how it looks, and this was Dungy, who was a pioneer in putting forward important qualitative ideas on reconnection at a time when Alfvén was vigorously opposed to it. Dungy suffered greatly from it. Alfvén was a great physicist, one who won Nobel Prize because of his work on MHD, but he totally believed in ideal MHD and was a very reluctant convertee to reconnection theory, something that Dungy paid a price for. But nonetheless, Dungy, like all good scientists, stuck to his guns, and time has proven him right. Here are two configurations I want to show you of the Earth's magnetosphere. One is the solar wind, which has the interplanetary magnetic field, but this is where the magnetic field, this is the interplanetary field southward, and then there is a case when the interplanetary field is northward. In the case of both cases, you're actually facing a situation where there are regions where in fact the magnetic fields are oppositely directed. When the field is northward, this does not occur in this region because field lines are pointing in the same direction. And it turns out when you really follow through, you find that reconnection actually occurs in very different places, more poleward than here. But when the solar wind is southward, you can see quite clearly that the direction of the magnetic field is opposed to the direction here, and it's actually ripe for reconnection in the sense that we have discussed earlier. The breakdown of ideal MHD occurs in a thin layer on the magnetopause. Implies now that by no means can we claim that the Earth's magnetosphere is completely shielded from the solar wind. In fact, the integrity of the magnetopause is, if you want to call it that way, as a complete barrier, is corrupted due to the effect of reconnection. And in fact, as you will hear in Professor Knipp's lecture tomorrow, you have times of very high geomagnetic activity, which have enormous implications for space weather, when the field IMF field is actually turning southward. In both cases, however, you have reconnection going on, and which made Dungy throw up his hands and say, but this is typical of him, he was a very humble person. Magnetoforce phenomena are more complicated as a result of merging, which he used as a substitute for magnetic reconnection. And this is why I no longer work on the magnetopause. But I hope many of you will, because reconnection is extremely important for how the Earth's magnetosphere actually responds and even lets plasma in. And here I am showing you a cartoon picture of what actually occurs for a substorm. And a real signature of substorm, as you have already seen, is polar cap brightening. This is in fact a spectacular picture using Viz camera. Professor Lou Frank at the University of Iowa pioneered this technique of actually having multiple missions carry missions. There's not a lot in the Earth's magnetosphere that we can image as we can for the sun, but the auroral cap brightening is one of the bright features for imaging, or bright accomplishments of imaging. And what you're seeing here is a cartoon picture of the bow shock of the magnetosphere, but then due to southward turning of the IMF, how reconnection actually allows for the transfer of flux going from the day side to the night side, leads to a thinning of the magnetotail, producing reconnection at distances of about 25 to 35 RE, as has been seen by numerous satellites. And this, in fact, leads us to the problem of substorms, in which I'll have more to say a little later. What is interesting is that the auroral oval that you see here marks the boundary between open and closed field lines. We call these black lines, pardon me, closed lines. And these are open lines in the sense that they're anchored on the ionosphere, but they go out to infinity. And so this that you see is in fact the boundary between open and closed field lines. And the reconnection rate, as Nick was alluding to, can be determined from radar observations of ionospheric convection. And so you have ground-based observations, which actually give you a lot of information on what the electric field is, which can be estimated from simply E plus V cross B equals 0 away from the diffusion layer, where VB gives you a very good measure of the reconnection rate. So what happens is that the Earth's magnetosphere features the interaction of collisionless magnetized plasmas. The solar wind interaction stretches the magnetic field lines into an extended tail, and this is what I'm showing you here. Excess energy and magnetic flux are stored in the magnetotail during this northward turning and then suddenly released. This phenomenon of sudden release of energy, which I call impulsive release of energy, is as common in the sun in solar flares, for example, than it is, as it is in magnetospheric substorms. And theories have a major burden on them that they must, if they are doing things accurately, not only show why a plasma goes through a very slow phase when things are only evolving slowly and energy is getting stored to the point when it is really suddenly to auroral brightening of the kind that you've already seen. And so Samuel Tatarika, who is a Jackery Fellow in the UCAR program, he came actually from Stanford University, where he used to work in SLAC on the high energy density physics program. He had the privilege to be his postdoctoral advisor, and he's at Princeton. So he actually did some absolutely remarkable three-dimensional, fully particle in cell simulations of the Earth's magnetotail. I want to make sure that you understand that I am not making claims here that are outside of the ordinary. There are many simulations of storms and substorms done by global MHT codes. or even by more high resolution MHT-based or fluid equations. What they do not do is to actually do fully three-dimensional studies of the substorm, where you take a particle in cell code, which has ions and electrons fully kinetic, and actually have them go in 3 dimensions. This is a very, very hard simulation. This simulation is the largest of its kind. It spans about 60 Earth radii with a dipole field. And what Sam was able to do was that he discovered this really obscure paper by Manankova. For reasons I have no idea, neither I nor anybody else in the space physics community ever picked up on this Russian analytic paper, which had solved for exact Vlasov equation equilibria of the Earth's magnetosphere and wrote down exact analytic solutions for it. So it made it really easy for him to load particles and static kinetic simulation, for which we have been using all kinds of approximate equilibria. But anyway, with that said, what he did was that he ran, by the way, notice this is not perfect at all, because you're looking at mass ratio of 25. The actual mass ratio for a hydrogen plasma is 2000, but this is the largest we can do of a magnetotail of this size. And ion, DI is the ion skin depth, and we are looking at Earth radius to DI of the order of 5. This too is a bit of an approximation, but not as bad as the mass ratio is. TI over TE of 5 is actually guided by observation. So the two-dimensional results are that if you don't vary anything in 3 dimensions, what happens is that if you drive it with a dawn-dusk electric field, you thin down the current sheet, and you actually form X-line-like objects like we were discussing at about 35 RE or so. From this then emerges what is called flows occur, both tailward and earthward, which is also sunward. And they carry with them what is called a dipolarization front. You have a front. This was actually discovered by Themis. The front moves inward. And what is Sam seeing here is that in 2D, this thing reconnects and the front propagates inward, just as it is reported in Themis. But that by itself is not enough to cause substorm at nearer distances. People have shown through very accurate detective work on satellites, and there's universal agreement on this, that the most important substorm onset phenomena actually occur at nearer distances of what 10 RE, not just the reconnection X-line forming at 35 RE, but the time it takes from the formation of that to when it actually disrupts. But when it goes to 3 dimensions, and these are, by the way, times in cyclotron orbits, he sees very strongly Y-dependent perturbations of the cross-tail current. The reconnection dynamics on 2D are qualitatively similar. The current sheet flapping motions modulate the thin current sheet, but what 3-dimensional instabilities are what causes the disruption. And field-aligned current is produced, and the cross-tail current, which he actually plots, at distance of 10 RE, goes through this sort of a phenomenon and then suddenly disrupts in 3D. And that, if it were not for the inclusion of 3D effects, we do not get this catastrophic disruption in the current. And it's our suggestion that this has been caused by a kinetic ballooning instabilities. For those of you who do not know what that means, it's really a kinetic pressure-driven instability that is causing this sort of current disruption, not reconnection per se, even though reconnection was the initial driver that caused the flows. Things go ballooning unstable, and reconnection eventually does become important, but there is an interplay between reconnection and pressure-driven instabilities in the near-Earth regions. One of the advantages of a fully kinetic study is that you see particle energization. So in this study, Sam was able to track the deviation from Maxwellian distributions that he loaded the system with and how it becomes more heated. And this is not inconsistent with our knowledge of what we did when we were discussing particle acceleration. And I just want to quickly flash this by you. I mean, we did talk about particle acceleration, and what I want you to keep in mind, and I can't go into it too much further, is that there are various sources of acceleration in the Earth's magnetosphere. What I talk to you about here is tail reconnection and acceleration. Auroral acceleration, as I mentioned earlier, has other explanations and theories and observations that go with it. Then there is shock acceleration, which we covered in our lecture and also in the lectures that came after. This does not by any means cover everything that we can do. Inner magnetosphere itself, through ring current, through radiation belts, they all have their own sources of acceleration. Wave particle interactions are very important in these. It's too much to cover in one course, but just so that you have a glimpse of how what we learned fits in the broader context. How much time do I have, Dana?
Oh, you have at least 15 minutes.
Oh, that's good.
Maybe more.
Okay.
We end at 11:30 or do we end at 11? I think we end at 11:20, so you have 15 minutes.
Okay. Any questions at this point?
Amitava, could you expand a bit on how the balloon, like where exactly in the inner regions the balloon instability has the most significant effect, or is currently thought to
Sure,
have?
I'll be happy to. It's a favorite subject, as you might have gathered. So what happens, you know, the reason I think there has been a lot of substem controversy, and these controversies were there even before I knew anything about space physics. So all that I can tell you is that I didn't have a hand in causing them. But I think that people did not do very careful theory. Sorry to say, I don't like to, in a field in which dominantly observation driven, it's too vain for theorists to claim that they drive anything at this mature stage of the field. But on the other hand, what really happened was that people thought that reconnection is what is going on at near Earth distances. And by the way, if you do two-dimensional models, you find that you get reconnection at far distances, or what I call mid-tail distances, but also at near Earth distances as the current sheet penetrates and the BZ field on the axis becomes a very small value. There is no doubt in my mind that if there is no 3D instabilities that intervene, that the 2D picture of reconnection is a perfectly valid picture. And it probably happens too. But what happens sometimes in the dipolarization observations, that you look at the BZ component of these dipolar fronts, they're pretty large. What that BZ thing does is to suppress reconnection to a very large degree. And you say, is there another instability that can happen that could just get rid of this BZ and the pressure gradient that is building up? And that's the nearer distances. And pressure gradient, when it couples with bad curvature, and this is what is bad curvature of the magnetic field, is where is the ballooning instability become important. Now, one of the signatures of the ballooning instability is that it must have a Y dependence, the Y dependence perpendicular to the plane of the paper. And it has an ideal image diversion. It has also a kinetic version where the most unstable wavelength is inverse Larmor radius. If you look at Sam's observations, that's what we are seeing. As opposed to reconnection or kink type of instabilities, which tend to have much longer wavelength. Based on simple checks of linear stability criterion, this is the region then in the region of 10 RE where we are saying that under certain conditions, ballooning could play a role. And it sort of puts together the sort of out-in, in-out picture in a way that drove the Themis mission. What we are really saying that a thin current sheet is very unstable. A number of things can happen which will destroy that current sheet. Maybe sometimes you have the analog of the X line forming at 10 RE, but a lot of the times you may not. You might first get an ideal instability that then actually will pave the way for reconnection to actually break off a plasmoid and send it down the tail. Do I make sense?
Yeah, that does make sense. Can I ask to clarify just that, you know, you mentioned the argument about the out-in sort of thing. What you're kind of suggesting is that the picture is so complicated in 3D and the interplay between certain instabilities and reconnection might be so complex that it's hard to think of it, or it's perhaps invalid to think of it as an in-out, out-in sort of?
I would say that is what I am saying. I'm saying that
Okay.
either of those pictures have polarized the community, and it is unnecessary. Because I don't have a big axe to grind. You know, I'm a big fan of reconnection myself, and I wish I could tell you that in all our simulations, reconnection seems like the trigger. No, when we actually have done a careful analysis of thin current sheet equilibria, and we find that they're often ballooning unstable, especially because the beta is so high, between 10 and 50. It's not hard for this to happen, even if reconnection hasn't occurred. The in-out picture of Tony Louis and others argues that you don't need anything happening in mid-tail at all. Just left to itself, the magnetotail will spontaneously disrupt if something happened at 10 RE and propagating out. This we haven't seen happen in our simulation. We find that something is triggered at 35 RE, but then what's going on deep inside could have a complicated interplay of instabilities and reconnection. Make sense? Okay.
Yeah, I think so, thanks.
All right, thank you. Let me now get to planetary magnetospheres. I have learned a lot from Fran Bagenal's papers and other, her lectures and everything. So I've liberally borrowed from it. This is in fact your classic planetary system, giving you the distances, various AUs. This is our dear planet, exactly at 1 AU as AU is defined. And you have all these other planets. Pluto, as you know, has been dethroned, no longer regarded as a valid planet anymore in the minds of many, and probably with good reason. One thing that I wanted to prepare you for is that there's a big thing that I haven't discussed with you, which is the origin of magnetic fields in planets, including our planet Earth. This is what is called the dynamo problem. I would love to talk to you about the dynamo problem because it's a problem, not only an unsolved problem for most planets and sun, but also for most astrophysical objects. It's an absolutely favorite topic, but it can easily take an hour. We postpone it to another day, another summer school. But what this picture shows is that if you think of the source of a magnet and very crudely approximate it by a bar magnet, which it absolutely isn't, then you see a rotation about the axis and a magnetic axis defined by the alignment with the north-south connection. And that's the dotted line. And what you're seeing here is the rotation axis of these planets. And what this simple view graph does is to make the point to you that even allowing for the offset between the magnetic axis and the rotation axis, the dipole is a rather poor approximation. In fact, much better magnetic field models exist where you go to Jackson and you expand everything out in spherical harmonics and calculate coefficients higher order than the dipole, and those corrections are very significant. Nonetheless, the dipole magnetic field in the solar wind is not a bad model, and the Chapman-Ferraro distance has been the beginning point, and I don't have to apologize for quoting this formula to you because Dana already has, and you've actually derived it. But this Chapman-Ferraro distance is a good proxy, in fact, for you, for the distance of the magnetopause with respect to the radius of the planet. And when you actually calculate that for Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune, one thing you quickly realize is that for Earth, the RMP calculation gave you something of the order of 10 RE, which lies between 8 to 12 RE. And I pointed out to you why the corrections due to various things, not included in Chapman-Ferraro, can make up for the distance. But in the case of Jupiter and Saturn, notably, the deviations are significant. And what you notice is, in fact, for Jupiter and for Saturn, these are significantly larger than the prediction of the RMP calculated by the Chapman-Ferraro-like formula. The other ones are not bad, and there is a special physical reason why this is off. And where this is off is the source, this basic physics that is there for the Earth's magnetosphere, which is that you have the solar wind on the outside and some penetration within. So to leading order, we balanced off the magnetic energy and the solar wind. But what you really have is that you have this moon Io, which produces an enormous amount of plasma, tons and tons of it in Jupiter's atmosphere, and is constantly loading it with plasma. Ganymede and Callisto are two moons of Jupiter here, along with Io shown in the picture. We know a lot about Io and Ganymede thanks to space missions. But what really happens is that you still have the classic picture for the Earth's magnetosphere. Everything is much larger when you get to Jupiter. I mean, Jupiter, as you know, in astrophysics terminology, is a planet and not a star. It's a frustrated star because it came so close to becoming one, but never really had enough neutronic fusion going on in its core to actually produce, to become what the sun is. But what you're really seeing there is a balance, not only between the energy of the solar wind and the magnetic energy, but a large component of the thermal plasma for which Io is in fact the dominant culprit, loads Jupiter with a lot of plasma. So when you do that, the magnetopause actually moves over to larger distances than Chapman-Ferraro would predict. And so here is a list of plasma sources for Mercury, for Earth, for Jupiter, Saturn, Uranus, and Neptune. You're looking at particle compositions. And if you look at Jupiter, Earth varies, of course, and oxygen and hydrogen from the ionosphere, as Dana talked to you about, provide major composition for the Earth's magnetosphere. In the case of Jupiter, is mostly what comes out, oxygen and sulfur from Io. Enceladus is moon of Saturn, which plays an analogous role as Io does for Jupiter, and populates with oxygen, some amount of water and hydrogen. For Uranus, which is beginning to have more and more simulations done, it's actually the ionosphere. For Neptune, it is the Triton moon and the ionosphere which provides these. And if you actually look at the kilograms per second, if you look at Earth, if you look at this, what this amounts to mass loading of Earth of a few hundred tons. This is 5 kilograms per second. And if you look at the solar wind pressure, one of the things that you could wonder, the solar wind pressure is enormous. As to why it is that solar wind pressure completely doesn't blow off the Earth's magnetosphere is because gravity for a 200-ton object is pretty significant. So it provides, and Vasilianius has given some good estimates of this in his articles, on how that plays a role on that scale, keeping the Earth's magnetosphere where it is. So the aurora picture that you saw for the Earth is also seen in Jupiter and around Saturn. X-ray aurora observed by Chandra telescope around Jupiter. The UV aurora has been observed around Saturn. It has also been observed in radio around brown dwarfs. In fact, in pulsars, which are objects of very, very high magnetic fields, it's strongly believed that you get auroral emissions as well, except that because the pulsar is such a heavy object, it warps space in its vicinity, and corrections due to general relativity make a very important contribution to how it deforms the light signal cones that are emitted from pulsars. But believe me, magnetospheric physics, to the extent that we know about it today, even in the non-relativistic realm, teaches us a great deal that plasma astrophysicists can learn from. And of course, as I pointed out, people need to worry about space storms when it comes to habitability on exoplanets. And on that note, I end my talk. I thank you very much for putting up with this, my long lecture, and hope you had fun. Not nearly as much fun as I have had, I'm sure.